So one of the major themes that we have going into Chapter 5 is this idea that we're going to be working with logarithms. And so before we can really do any calculus with logarithms, I have to make sure that you guys are comfortable just working with basic logarithms. And so I want to start with a really easy question. And that question is, what is the log base 2 of 8? Right? And if you've forgotten your logarithms, then the thing I need to tell you is that logarithms are effectively all about powers. What this question here is effectively asking is it's saying 2 raised to what power would give you 8? When you think about it in that light, it's really easy. You realize, oh, it would just be 2 to the third power, which means that the log base 2 of 8 is 3. So what about something like the log base 2 of 4? Well, again, we would understand this means 2 to what power gives me 4. So clearly that's 2. I could ask a couple of other interesting questions here. One of which is this one. The log base 2 of 1. What's interesting about it is that you'll find, if you think about it, that the log base anything, like 2, log base 2, log base 5, log base 17 of 1, is always going to be 0. Because what the question amounts to is 2 raised to what power gets you 1. And you guys know that basically anything raised to the 0 power is 1. We can ask a couple of other little questions related to this one. What about the log base 2 of 1/2? Well, if I was going to raise 2 to a power and get 1/2, I'd have to raise it to a negative power so I could turn it into a fraction. So this will end up being negative 1. And I can do this with many other fractions. You know, for instance, I could do the log base 2 of 1/4. Alright, and here you're saying, okay, 2 raised to what power get me 1/4? That'd be negative 2. Another interesting problem, I suppose I'll put the interesting problems into this section over here. Not that they're really different, but that they're things that are sort of universal and are going to apply. What if I were to ask for the log base 2 of negative, to be honest, anything, negative 4 even? This question is asking 2 raised to what power is negative 4? And the answer is there's no real number that you can raise 2 up to in order to get negative 4. Now, those of you that are listening particularly carefully, I did say no real number. You can use imaginary numbers to do it, but we're just going to run and hide from that. For our purposes, this is undefined. You don't need to worry about it. I'm not getting into it at all this year, and it's not necessary. So good, we have this basic sense that this is what these logarithms do. Now, I said that I wanted to talk about evaluating logs and also logarithmic graphs. So now that I've got a lot of different data points for the log base 2, I kind of want to look at what the graph of log base 2 looks like. So if I were to ask us to graph y equals the log base 2 of x, I guess my hope is that we could plot a bunch of those points that we just came up with and see what we can get, right? So from up above, we knew that when we plugged in 8, we got back 3. When we plugged in 4, we got back 2. So we can apply that down here. So if this is 1, 2, 3, 4, 5, 6, 7, 8. So when we plugged in 8, we got back 3. When we plugged in 4, we got back 2. When we plugged in 2, we got 1. Plugged in 1, we got 0. Plugged in 1/2, we got negative 1. Plugged in 1/4, and we got back negative 2. And further, we remember that if we try to plug in any negative number, it's undefined. That means you're never going to have anything to the left on one of these graphs. And so I can just sort of connect the dots here. And we end up with a graph like this that basically has an asymptote here on the y-axis. And so that's what your basic logarithm graph looks like. The points that I really want to draw attention to, I feel like there are really a few things that help you to draw any logarithm graph well. The first one is this point right here. The question is, what's special about that point? That point right there, being the point 2, 1, is sort of a graph that says, you know, whatever the base of the logarithm is, when that thing comes first, you're going to get a 1. Right? And the other point that's always important is this point right here, because the coordinates of that point are 1, 0. For any logarithm graph, you're going to pass through 1, 0, because when we take the log base 2 of 1, or the log base anything of 1, you're going to get back 0. So let me scroll this up and take a look at sort of one more of these graphs then. What if I were to ask us to graph y equals the log base 5 of x? Right? Now, I had identified the idea that there were those two important points. So one of them is at 5, 1. And again, think for a moment about why that point makes sense. It makes sense because when I plug in the x-coordinate of 5, when I plug in 5 right there, somebody's saying, hey, what's the log base 5 of 5? What power do I need to raise 5 up to in order to get 5? Well, 1. Right? The other point that's important is this one, because we know that when we plug 1 in there, we're going to get back 0. And then we mentioned on the previous problem that on the y-axis we get this vertical asymptote. And so we can sort of imagine that this logarithm graph is going to look like this. So it's effectively the same shape as the previous one, but this one is growing more slowly because it's a log base 5 and not a log base 2. So the one other thing I was going to throw in here, and I don't want this video to be very long, actually I suppose there are two things I need to throw in here, is one, so what about shifts in these graphs? Right? What happens when somebody asks you to do y equals the log base 3 of x plus 2 plus 1? Right? My take on it is I kind of want us to ignore the plus 2 and the plus 1 for a moment. Just take a minute and figure out what the log base 3 of x looks like. So if you'd like to pause the video and kind of do that on your own, please do. Okay, so the log base 3, our two important values are going to be 3, 1. Maybe I should do this in a different color. 3, 1 and 1, 0. And so we sort of have a sense, and there's the vertical asymptote, right? Yay. So there's this sense that this is what the log base 3 graph looks like. You know, y equals the log base 3 of x is sort of this dotted, misshapen, function that I have. But because I have these two important values, and because I have this vertical asymptote, I can perform these shifts on them. And hopefully you remember that the plus 2 here means the graph is going to go to the left by 2, and the plus 1 at the end here means the graph is going to go up by 1. So I can just take these points that I had and shift them accordingly. This point here will move 1, 2 to the left and 1 upward. This point here will move 2 to the left and 1 upward. And even the vertical asymptote will move, 1, 2 to the left, and then it'll move 1 upward, but because it's an infinitely long vertical line, that doesn't actually mean that was awesome, that I just undid the graph that I had drawn there. Sorry about that, everybody. Still learning this program a little bit. What we had was this point at 3, 1, the point at 1, 0, and the vertical asymptote. And we had said that we were going to shift these points 2 to the left, 1 up, 2 to the left, 1 up. And then the vertical asymptote, which I'm not going to undo this time, this thing shifted to the left 2 and up 1. So I'm getting this vertical asymptote over here. And we can draw our log base 3 shifted graph. And yay, we did it. We've got this graph of the logarithm. The last thing I need to say, and like I said, I really didn't want this video to be this long, but this is an introduction. We do need these pieces. Is that, to be honest, we're going to spend very, very little time in Chapter 5 working with log base 2, or log base 3, or log base 8. Because in a calculus sense, they're actually pretty ugly. The log we're going to spend the most time on is the natural log. Right? The natural log is the one that looks like y equals ln of x. And all it means is that you're looking at the log base e of x. Now, we're not ever going to write it that way. I'm never going to write log e of x. I'm always going to write, you know, ln of x. But understand that that's what it means. All it means is that we are working with this base of e, and e is Euler's number. It's the number 2.718. And it goes on forever. It doesn't have any patterns or repeats. But that's basically what it is. Because e is 2.718, we can have a sense of what that graph looks like. It means you're going to have a point over 2.7 and up 1. And a 0.10 in your vertical asymptote. That's what the natural log graph looks like. And what's really kind of funny is that all of the questions I'm going to ask you for are going to be pretty simple. For instance, what's the natural log of e squared? You're like, wow, you know, what power do I have to raise e up to get e squared? Well, I'm pretty sure that's 2. Right? What's the natural log of e cubed? Well, that's 3. What's the natural log of e? What power do I have to raise e up to in order to get e to the first? Well, the first power. Right? So that's our basic introduction for graphing these things, for evaluating logarithmic functions. Sorry the video was long. Sorry I erased that thing in the middle of it and that my voice sounds terrible because I'm sick. I'll see you in the next video.